Hello grade 11s, this is a video to look at 7.8 two-sample tests. Up to this point we've looked at two types of one-sample tests that we can do using the Inference app. The first was the Z test and the second the T test. Hopefully you remember the important difference between the two. If we know the population's standard deviation or variance, we can use the Z test. If we don't know it and we're having to estimate it based on the sample we've got, we need to use the t-test. One works from the normal distribution, the other works from the t-distribution. Today we're going to look at two types of two-sample tests that we can do. They're quite different. We'll look at when we choose each one, and we'll look at how we treat them differently. So one of the main uses for the t-test is in comparing two different samples and asking if they could have come from the same population. The assumption is always that the distributions are the same and the standard deviations are equal. So the test is just whether or not the populations they come from have the same mean. As before, you have to consider whether x bar can be regarded as being normally distributed before carrying out the test. So we've talked a little bit before about exam questions, and I think we looked at saying most of them would be around about 6 marks, but there's lots of little extra questions that you can be asked, one of which is stating any assumptions you're making. And for this test, one of the assumptions you might need to make is that the data that they come from, the population they come from, is normally distributed. You might have a big enough sample size so that the central limit theorem applies, and then that's not such a concern. But clearly you can see from the example below, we're not going to have 30 pieces of data here. So it's going to be an assumption we're making. So let's move on to this example. Mr. Arthur gives his two chemistry groups the same test. He wants to find out if there is any difference between the achievement levels of the two groups. And the results are in the table. You can see that group 1 has 2 more students than group 2. The data doesn't seem to be in any order. I guess maybe Mr. Arthur just wrote the scores down and the students were arranged alphabetically or somehow. So there's nothing special about the way the data's been written down. And we're trying to compare group 1 and group 2, trying to decide whether one of the groups is stronger than the other group. Okay, so we do not know the population's standard deviation, so we're going to be having to do a t-test. We have 2 samples here, so we're going to be doing a 2-sample t-test. We are going to start by writing down our hypotheses. That's always how we're going to start hypothesis testing. So we're going to introduce some variables that we're going to use. We're going to let mu1 equal the mean for group 1 and mu2 equal the mean for group 2. Up until now we haven't had to define mu because mu on its own is a recognised symbol, certainly within the IB curriculum. Mu1 and mu2 are not, so you do need to define what they're standing for, even though in this case it's very obvious from the fact that it's groups 1 and groups 2 and we're doing mu1 and mu2, but it is an important step in terms of trying to be thorough with your notation. So write down the null hypothesis. The null hypothesis is that they're always going to be equal. Remember, our mean needs to be equal to something for a null hypothesis, so the only option is that the two means are equal. To get the alternative hypothesis, we need to look, are we deciding that, is he checking because he thinks one is stronger than the other, or are we just seeing whether they are the same? So if we reread the question, and it says he wants to find out if there is any difference. So there's nothing in the questions to suggest that one group is stronger than the other. So we're going to say that we want to find out whether they are equal or not equal to each other. So this is a 2-sample, 2-tailed t-test. So perform a t-test at the 5% significance level. This is one of the nicer t-tests where you've got the raw data. It's a bit time-consuming entering the data, but it means you don't have to calculate the unbiased estimate of the population's standard deviation. The calculator does it for you, which is always nice. So we can put this data into one variable stats or two variable stats and import it. It makes more sense to put it in one variable as it's one variable data. I've already done that. I have checked my data to make sure I haven't made any mistakes in entering it, because I probably wouldn't, unless it's something glaringly obvious, I probably wouldn't notice it from my results. So if you want to, it probably makes sense if you pause the video, enter the data yourself so you can work along and get used to what we're doing with this. So I'm going to go to the Inference app and I'm looking at hypothesis test. And we need to look at the types. So we've done the one sample Z test. We've looked at the one sample T test. Today we said we're doing a two sample T test. And the alternative hypothesis is that they're not equal. So we set that front screen up, and that's really important in making sure that we're going to get the right values from our calculator. Okay, I'm going to press the table button, and I'm going to import my data. So I'm going to import one variable, stats, column 1 and column 2. Obviously you don't want the same column twice, otherwise I've got the same data. And a nice quick thing to check here is I've got 14 pieces of data from the first group and 12 from the second. Okay, so that's all entered now. I'm going to keep the significance level at 5%, and I do want to pool my data. For all of your exam questions in the IB, you will be pooling your data. What that means is that we are assuming that the two samples have the same standard deviation. So that is something that will always happen in your exams. Okay, so it's all set up now, and I press Calc, the bottom right of your screen, and I get my results. So the one we're looking for is the p-value. P-value is very high, so it's definitely not a significant result. If we want to check, we can look at this, fail to reject HO. Okay, so I'm going to state, this was part A, wasn't it? I'm going to state the p-value, 0.816 when we round it. And we know that that is much bigger than 0.05. Okay, and of course we need to conclude this. So there is insufficient evidence to reject HO. And then we should conclude it in the context of the question. So if we're not rejecting HO, if we're accepting HO, it means that the mean for group 1 and group 2 are the same. So Mr. Arthur's two chemistry classes do not seem to have a difference in achievement levels. So we can say something to that effect. The two groups do not have different achievement levels. Okay, so that was the two sample test. Obviously, it could be set up differently. Maybe you're given the statistics rather than the raw data, and you might need to calculate that unbiased estimate. But yeah, we're always going to make sure that we are pooling the data down here. And yeah, just being careful to set up that initial thinking through that initial screen. Okay, so that is the first of the two sample tests. There's a little note up here about the pooling, but we've already talked about that. If you want to pause the video and have a go at one of the first homework questions, that might be a good idea. If you are feeling ready to go straight on to something that is slightly different, then keep going. So the second type of two sample test we're going to look at is a paired sample test. And this is a special type of two sample test because we use this when the two samples are paired in some sort of obvious way. And what we end up with is a slightly more rigorous test. So when I say paired up in some sort of obvious way, it means that instead of having two separate groups, maybe we have the same group and we're looking at them doing a chemistry test and a physics test, and we're seeing if they're stronger in chemistry or physics. Or maybe we're taking these students and we're giving them a chemistry test, and then we're giving them like a intensive revision course, and then we're giving them another chemistry test and seeing if it's the revision course has worked. Or maybe it's a group of athletes that go on a training camp and then come back, and we can compare their time on a course before the training and then a time on a course after their training, and we can make a comparison. It's important that we're talking about the same group of people or the same group of objects when we're thinking about doing a paired sample test. So it's not enough just to have 12 students from group 1 and 12 students from group 2. They've got to be the same students. Okay, so the null hypothesis is the same in that we're saying that the two populations have the same mean, but we phrase it a bit differently in that we talk about we're actually testing the difference between the two samples. So what we end up doing is a one sample test, even though we're starting with two samples. So let's take a look at this. 5 candidates attended a revision course hoping to improve their chemistry grades. They were tested before the course started and were tested again at the end of the course. The results were as follows, and you can see that the scores are lined up. So student number 3, we can see, had 29 before the course and 33 after the course. So we can pair these two sets of data up. So we're going to determine at the 5% level whether the course improved the candidate's performance in the chemistry test. Okay, we're going to ignore this for now because I think we need to talk through it a little bit. So the first thing is we've got to define a variable which is going to be mu d, which is the difference, the mean, the mean of the difference. So let mu d be, it's already up here. We might as well keep that part. But I'm going to get rid of this. Okay, so you can choose how you calculate your difference, whether you do the score before the course minus after the course, or whether you do after the course minus before the course, as long as you are very clear what you are doing. So to make it clear, I'm going to do the after course score minus before. Okay, so that's what I'm going to calculate, their score after minus their score from before. So underneath this, I'm going to calculate 72 minus 64, 60 minus 43, 33 minus 29, 55 minus 56, and 62 minus 61. All right. My null hypothesis is, of course, that there's no difference. Yeah, that the before the course is equal to after the course. And what we want to check is determine at the 5% level whether the course improved the candidate's performance. Okay, if you go on a course and it improves your score, and you do your after course score minus your before course score, you want the after course score to be higher. That shows that you've improved. So what we should be finding when we do the difference is that these differences are positive, that they're greater than 0. So I'm going to say that mu d is greater than 0. If I had done this the other way around, if I'd done before minus after, and I want to see, and I'm looking for an improvement, I would be saying that I should be getting a negative result now. The score after the course is being subtracted from before the course. So it doesn't matter which way round you calculate it, as long as you are clear and you think about it. And you might have to really stop and think about what the appropriate alternative hypothesis is. So both of these would work, but I would need to have calculated them the other way round. I'd been doing 64 minus 72 is negative 8, for example. Okay, let's get rid of all this now. All right, so let's have a little think about what we're doing. I don't know the population standard deviation, so we're doing a t-test. It is a one sample t-test, or it's a paired t-test really. Let's call it a paired t-test. And it is one-tailed because we're only looking at whether it has improved, whether it's greater than 0. All right, I have got all the raw data, so I can enter that into one variable statistics. Let's go back here. I think it was 817 for -1 and +1. Okay, 817 for -1, +1. Okay, as long as my initial calculations were correct, my subtractions, that should all be in there correctly. So I'm going to do a t-test on this. I have, for the purposes of what we're doing, I have one set of data now. So when I go to my inference app, I'm going to go to a one sample t-test. My alternative hypothesis is that it is greater than 0, that there has been an improvement. And of course, my null hypothesis for this will always be that it's equal to 0, that there isn't a difference. So I've pressed the num button or the table button. I can input my data. I think I put it into column 3. Yep, there's my 5 pieces of data. Okay, so that's filled out the top 3 sections. The null hypothesis is 0, as we said, and there's the significance level. And now we can calculate it. There's my p-value, pretty close to being 5%, but it is still above. So 0.0713. Okay, so it is, once again, not a significant result. So it means we are not rejecting HO. So insufficient evidence to reject HO. So what does that mean in context? Insufficient evidence to reject HO. Okay, so we're accepting HO. HO was that the difference is 0. That means that there's not a significant improvement through doing this course. So it is not the result that they want to be, if this is the course who's doing this test, it's not the result they want to be finding. So the course has not improved candidates' scores. Okay, so once again, we've had to make the assumption that this data comes from normally distributed data. There's only 5 pieces of data, so that is an assumption that we've made. Okay, 2 quite different tests. Both deal with 2 samples, but they're both done quite differently. Whether we're looking at 2 samples and comparing them, or whether we're looking at these 2 samples and investigating the difference. For the difference approach to happen, we have to make sure that they are paired up in some meaningful way. All right, do have a go at practicing from both exercises. I think the first set, 14H, is the 2 sample and 14I is the paired, so make sure you're trying from both of those.